All right, this is unit 2.5 and the last subunit of unit 2. So unit 2.5 is about electromagnetic induction. And electromagnetic induction is the notion that generators or metal detectors and other stuff in our world is based on. So the first thing we need to know about electromagnetic induction is simply one equation, and this equation is flux equals BA. So this flux is called magnetic flux, and that's the symbol for it. And we already know that B is the magnetic field, the magnetic field strength. A is actually the area perpendicular to the direction of the magnetic field. Now this will be easier if we visualize it on this paper. So imagine there's a plate, a sheet, right, whatever it is, and there's a magnetic field going through it. Let's draw two lines. Okay. Now this will be a pretty weak magnetic field. Let's say it's 1 Tesla. Actually, 1 Tesla will be pretty strong, but let's stick with 1 Tesla. And let's say the area is 2 meters squared. Well, B times A is, in this case, is 1 times 2, and we get 2 for the magnetic flux. And the unit for flux is Weber, like the barbecue. So after learning about flux, we need to know a second equation that we use to calculate the voltage generated by the change in flux. So the equation is EMF equals change in flux. Now we're going to use delta sign for change, and flux is this, change in flux over change in time. Now let's write the equation for flux again. Flux is BA. Okay, let's start from the very top. So EMF stands for electromotive force. Now this is very tricky because despite being called a force, electromotive force is not a force, it's a voltage. So it's measured in volts and it's caused by a change in flux over a certain amount of time. And we already know that the equation for flux is BA. So a change in flux can be either caused by a change in the magnetic field strength or a change in the area perpendicular to the direction of the magnetic field. Now, these two equations are the fundamental principles of how a generator works. So a generator, if you have seen a generator, it's basically made up of magnets, permanent magnets that has a fixed magnetic field. Say it's going from north to south, from left to right, right? And there in the middle, there's going to be a coil of wire. And it's on a stick so it can spin. Now, why do we need it spinning? First, we're going to, first, the magnetic field is here, so there can be a flux. You know, the magnetic goes from left to right. So it's traveling this way. And so when this coil of wire is in the middle, it has an area, right? So the magnetic field is going through this area. But suppose that the wire is spinning. The wire is spinning in the middle. Now, every instance, if we measure its area perpendicular to the direction of magnetic field, say at t equals 1, now that area is going to be different every second. Say if we measure it a second later, it's going to be spinning at a different, it's going to be at a different place. So its area facing the direction perpendicular to the direction of the magnetic field is different. Thus, there's going to be a change in the magnetic flux. This changing flux induces a voltage in this coil in the middle, and the current driven by this voltage is called eddy current. Now, eddy current is just a fancy name for the voltage, the current driven by the voltage produced by this change in flux. So this is how a generator works, and you can actually also have a spinning magnet in relative to a coil that's fixed and not moving. That way, the magnetic field going through the area is also changing, because when you think about it, the magnetic field, although it's not changing, the area is changing every second. Anyway, there are videos on the YouTube and you can look it up. And the last thing we need to know is transformer. So transformer basically is, again, loops of wires and magnet. So it's something like this. And in real life, you're most likely to see this in a charger. You know the black box on your laptop charger, that thing is a transformer. And inside it this is a simplified diagram. Inside it there are coils. Let's give it 3 loops of coil on this one and say 6 on this one. 1, 2, 3, 4, 5, 6. There you go. So they're meant to be going around 6 times, and on this one is 3 times. Okay. Now we call this the number of coils on the primary number and the secondary number, N S. So there's a voltage going from here to here, right? Although they're not physically touching, it goes from this coil to this coil, and it works by the same principle, by changing magnetic field, but we're not going to talk about it today. The equation we need to know is that N over P, not N over P, NP over NS equals N, not N, VP over VS. Okay. So number of primary turns and over number of secondary turns is equal to primary voltage and secondary voltage. So when there's a voltage in the primary coil and when there's a voltage in the secondary coil, their ratio is the same as the number of primary coils over the number of secondary coils. Now we know there are 3 and 6. 3 on the primary coil and 6 in the secondary. Now if there is, say, 3 volts of voltage going through in the primary coil, we know that in the secondary coil it's going to the ratio is going to be the same. So in the secondary coil is going to be 6. Now you can also do other numbers like 1. Like 1 here. And we fill the number in, the number of, so 3 over 6 is 1. And to calculate the number of secondary coil, the voltage in the secondary coil, we simply do 1 over 3, 1 over half, which is 2. That makes sense. So this is how transformer, oh, by the way, I need to tell you what transformer does. So transformer increases the voltage or decreases the voltage. The one you see here increases the voltage from say 1 to 2, 3 to 6. And a transformer that increases the voltage is called a step-up transformer. Vice versa, a transformer that decreases the voltage is called a step-down transformer. So when do we want to increase the voltage? Well, before we do that, we need to know one equation. P equals VI. So the power is the product of voltage times the current. We don't want high current in our power lines. We want high voltage. So then in a case like that, we use a step up to increase the voltage and to decrease the current. So the power line could carry the electricity with high voltage and low current, so the wire doesn't melt. And say, why do we need a transformer for our laptop? Well, because the power point on the wall produces a different voltage to what your laptop receives. The voltage could be too high, too low, the current could be too high or too low. So a transformer is inbuilt into a charger to convert the voltage to suit the laptop. So that's how transformer works, and that's unit 2.5.